In the depths of a game meat processing plant, a side of venison slides slowly into a blast chiller. The surface still carries the faint tension of the animal's final sprint, but inside, the muscle fibers begin a silent transformation. Here, temperature is not a number, it's a force to be sculpted. Just like in deep tunnel freezing used in underground mining, where structural safety depends on carefully distributed cold, the shipment of wild deer meat requires more than refrigeration. It demands thermal architecture. Airflow, gradients, and insulation become as critical as any valve or sensor, because venison, unlike poultry or pork, resists cooling. Its dense myoglobin-rich tissue stores heat with persistence, delaying the descent to safe storage levels unless every thermal parameter is tuned with surgical precision. The science behind chilling venison is hidden from the supermarket aisle, yet it shapes the journey of over 4.3 million tons of meat every year. This is a triangulated global operation. Red deer and fallow deer raised or harvested in the forests of New Zealand, the meadows of Eastern Europe, and the controlled estates of Australia, destined for high-end markets in the Gulf states, Scandinavia, and parts of Asia. But climate doesn't cooperate. Between snowy fields and sun-bleached ports, the cargo passes through volatile temperature bands where a few degrees delay can mean cellular collapse. So engineers designed a solution that behaves less like traditional cooling and more like thermal harmonization. This is the intersection of biology, logistics, and engineering, where muscle memory must be frozen before it fades. To understand how this works, think of seed vaults in high-altitude agricultural research centers. There, moisture, oxygen, and temperature are calibrated to the millimeter, preserving life in suspended animation. Venison logistics operates under the same principle, except the timeline is faster, and the consequences are visible to the palate. A protein burn from uneven chilling isn't theoretical. It's the difference between a premium cut and a rejected shipment. And unlike domesticated animals, wild game carries more internal variability, more muscle tension, more environmental exposure, more microbiological risk, which means the first few hours after harvest are not just important, they're decisive. This isn't cold storage, it's cold strategy. Each container, each pallet, each slab of meat must pass through a calculated choreography of cooling, where internal core temperature drops in harmony with surface drying, and airflow must avoid freezing the outside before the center responds. In some systems, thermal blankets line the crates to slow down edge chilling, buying time for internal gradients to equalize. It's the same logic behind the insulation layers used in tunnel reinforcement for permafrost mining, where temperature shock could fracture a mountain wall. In meat, the fracture is microbial, enzymatic, invisible, but just as destructive. So before venison ever crosses a border, it crosses a line of engineering thresholds: biochemical, mechanical, logistical. The work is quiet. The sensors hum, the steel doors close, and deep inside those moving cold chambers, temperature doesn't just preserve meat, it preserves the value of a global trade, a trade that depends not on haste, but on harmony, not on power, but on precision, because in this system, meat doesn't travel, temperature does. 3 hours. That's the invisible window that determines whether a harvested deer becomes a premium export or a costly loss. From the moment the animal is brought down, an irreversible clock begins to tick. In the world of venison logistics, this window is sacred, and it's as much about physics as it is about biology. Game meat, particularly from red and fallow deer, begins breaking down the moment ambient heat, muscle tension, and enzymatic activity interact without intervention. When external temperatures rise above 10 degrees C, the rate of degradation accelerates exponentially. In just a few hours, the texture begins to loosen, discoloration sets in, and the meat's internal chemistry shifts beyond recovery. The challenge is geography. Most wild game isn't harvested near a chilling plant. It's taken from open terrain, forests, plateaus, or scrub-covered hillsides, sometimes dozens of kilometers from the nearest refrigeration hub. That distance used to be the weak link, but over the past decade, technology has moved into the field. Literally, Mobile rapid chill units mounted on all-terrain 4x4 platforms now accompany harvest teams. These aren't makeshift coolers. They're engineered microplants, capable of drawing down carcass temperature to 4 degrees Celsius in under 90 minutes, using forced convection, sensor-regulated airflow, and thermal partitions. The result is not just preservation, it's preconditioning. By lowering internal heat early, these units reduce cellular stress and stabilize pH, setting the foundation for export-grade quality. In Slovakia, a multi-year comparative study tracked spoilage patterns across different harvesting protocols. The results were clear. Venison pre-chilled within 2 hours had a 42% lower spoilage rate after 2 weeks in refrigerated transit, compared to carcasses that remained unrefrigerated for over 5 hours. But numbers only tell part of the story. In Australia, a suspension of export permits was triggered when meat pH values exceeded threshold. After weeks of investigation, the root cause was traced to a simple oversight. Summer harvesting had been conducted too late in the day, without immediate cooling. The temperature gradient was wrong, the chill curve delayed, and the meat, though legally harvested, was chemically compromised. To avoid this, operators today treat chilling like they treat forage compaction in silage. The same principles apply: minimize oxygen exposure, compress the timeline, and equalize internal distribution. Cooling must be fast, uniform, and total. A partial chill creates a false sense of security, allowing microbial pockets to thrive undetected. That's why experienced handlers talk about chilling in layers. First the surface, then the muscle, then the core. Each with its own timeline, each needing its own flow of cold. And the equipment reflects this precision. Insulated carcass hangers, variable speed fans, even GPS-linked monitoring systems that log temperature drops in real time. These are not luxuries. They are the scaffolding of a meat economy that travels thousands of kilometers without margin for error. 3 hours. It's not a deadline. It's a design principle. From harvest to chilling, the logistics must move like synchronized machinery. Because in venison, freshness isn't a finish line. It's a starting condition. A starting point built not with haste, but with calculated urgency. In this supply chain, what happens in the first 3 hours defines the next 3 weeks. Inside the steel walls of a refrigerated container, 20 tons of venison rest on wooden pallets, bound for port. The refrigeration system hums steadily, numbers on the digital panel holding at a strict 1.5 degrees Celsius. From the outside, everything seems under control, but inside the stacks, at the center of the load, temperature tells a different story. Because cold, contrary to common belief, doesn't distribute itself equally. Without controlled airflow, even a perfectly calibrated reefer becomes an uneven battlefield of temperature zones. The edges overchill, the cores undercool, and in between, bacteria find refuge in thermal shadows that algorithms never predicted. Venison, like all meat, is thermally sensitive. But because of its lower fat content and higher internal variability, even small inconsistencies in cooling can accelerate shelf life decay. That's where airflow design becomes a hidden form of engineering. In the most advanced logistics chains, computational fluid dynamics, or CFD, is now used to simulate the precise movement of air inside loaded containers. These aren't theoretical exercises. CFD generates 3D maps that reveal airflow bottlenecks, pressure imbalances, and hot zones invisible to the naked eye. Based on these simulations, engineers adjust pallet spacing, insert baffles to redirect flow, and calibrate fan velocities to ensure every crate receives the cold it needs. The results are measurable. In a controlled experiment comparing traditional bulk-loaded containers to CFD-optimized ones, thermal hotspots were reduced by 76%. That difference translated into a 6-day increase in viable shelf life. 6 days may not seem much, but in global trade, especially involving fresh meat, it's the margin between retail distribution and landfill. Logistics teams from Estonia and Germany recently collaborated on this very challenge. German importers were receiving venison shipments that met all surface-level checks, yet showed microbial imbalances on arrival. The issue wasn't the temperature setting. It was airflow stagnation at the pallet center. Through CFD remapping, they redesigned the container layout, reducing rejection rates by half. This is logistics at its most invisible. Cooling that seems uniform, but isn't. Containers that look identical, but perform differently. And it's not about cooling harder. It's about cooling smarter. Air doesn't obey intention. It obeys physics. Without channeling, without calculated resistance, it clings to the periphery and ignores the core. The result is a chilling process that looks successful, but fails at the microbial level. And when that happens, no certificate, no label, no protocol can undo the damage. In the transport of venison, airflow isn't a variable. It's a design feature. Temperature must be distributed, not just delivered. Because meat doesn't spoil in theory. It spoils in corners, in gaps, in places where circulation gives way to stagnation. And in a world that moves millions of tons with thermal precision, there is no room for statistical cooling. There is only engineered cold, or there is spoilage. As one logistics director once said, if you don't map airflow, your cooling is statistical. Your spoilage is inevitable. In the silent geometry of the cold chain, meat is not just mass, it's matter in transition. From the moment venison leaves the field, every gram becomes a thermal object. It holds heat, releases it, absorbs cold, and resists equilibrium depending on its structure, muscle density, and surface area. This geometry dictates how temperature penetrates, how long it takes to reach microbiologically safe zones, and how consistently that state is maintained across thousands of kilometers. And in the case of wild game like venison, lean, dense, and often irregularly shaped, the stakes are higher. A single degree off at the core can determine whether a shipment meets export certification or is flagged for contamination risk. Venison harvested from free-ranging deer in Lithuania, Slovakia, or New Zealand doesn't follow industrial uniformity. The cuts vary, the environmental conditions shift with the hour, and the ambient temperatures at pickup points can fluctuate wildly. This means that chilling is not simply a matter of lowering the container's air temperature. It is the science of shaping cold to fit meat that resists simplification. The concept is known among logistics engineers as thermal geometry, the interaction between physical form, airflow distribution, and time. Where a box of uniformly sized pork loins may chill in minutes, a bulk load of venison haunches requires a slow, controlled descent that avoids freezing the outer layers while still pulling heat from the interior. If rushed, the surface develops ice crystals while the inner muscle remains in the bacterial danger zone. If delayed, enzymatic degradation begins. Neither option is acceptable. This is where innovation steps in. In Lithuania, cold chain logistics companies have begun using hybrid solar-electric containers equipped with phase change materials, substances that absorb and release energy during physical transitions, to modulate internal temperatures without overloading the power draw. These containers respond to the environment. As a truck climbs into alpine altitude or crosses a coastal microclimate, onboard sensors monitor not only the ambient conditions, but also the thermal behavior of the cargo. If a section begins to cool unevenly, the system adjusts airflow, activates backup cooling cycles, or repositions internal shutters to ensure uniformity. It's a kind of mechanical instinct, responsive, autonomous, and essential for long-distance consistency. This capacity for adaptation is not a luxury, it's a necessity. Global venison trade spans routes that connect the cold valleys of Eastern Europe with the high humidity of the Gulf states. Along the way, the meat may transit through desert tarmacs, fluctuating sea-level climates, and congested customs terminals where delays threaten the entire chilling curve. A passive system would lose the race. An intelligent one, shaped by data, geometry, and engineering foresight, preserves not just the meat but the economics behind it. Like a seed drill adjusting depth by millimeter in response to soil hardness, the venison cold chain is calibrated to the minute, to the contour of the cut, to the time of day and atmospheric load. It is a choreography where thermal gradients must remain in balance even when the cargo moves between time zones and thermodynamic pressures. It is agriculture's answer to physics in motion. This is not about refrigeration. It is about temperature as a navigable terrain, mapped, monitored, and manipulated like a resource. And in this terrain, venison becomes viable not through brute force, but through thermal finesse. What moves across borders is not just meat, but the result of a chain of precise decisions, each one aligning biology, logistics, and engineering into a single mission. Because in this system, food doesn't survive on distance. It survives on discipline, and that discipline turns temperature into infrastructure, geometry into security, and cold into continuity. That's why 4.3 million tons of venison don't just travel, they arrive.